Live from the Orion Cygnus arm of the Milky Way galaxy, this is Scientifically Speaking, a weekly half-hour program devoted to elegant curiosities, and I am one of your hosts, Sarah Chang, and joining me as always is Bernie Rhyme, DJ Star Watcher. How are you, Bernie?
Yes, hi Sarah, very good, thank you.
Bernie is our professor of the Astronomy Lab at USM and our local protector of the night skies. Reach out to us at WMPG Scientifically Speaking at gmail.com or on Twitter at WMPG SciSpeak. And you can go to wmpg.org to check out the last 5 episodes of all of your favorite shows, including this one. Bernie, what's up in the night sky for this coming week?
Okay, certainly, thanks. So this will be Friday, April 30th. So we're going to have a waning gibbous moon. The full moon was back on the 26th, so it's 4 days after full moon. So it's going to rise roughly around midnight. So unless you're up late, you probably won't see it. So we have another planet that finally joined Mars in the evening sky. So Venus has finally reappeared. So we can see Mars and Venus now in the evening sky. It was missing for several months. And then if you like to get up early, you can still see Jupiter and Saturn in the morning sky. So we had a meteor shower about a week ago, and there's nothing really coming up again until May. But you can always see some stray meteors. If you're out for like an hour at a time, you can probably see 2 or 3 meteors and lots of different satellites and things. So I always encourage you to get out and welcome back our sister planet Venus. Yeah.
Awesome. Thanks, Bernie.
You're welcome.
And if you couldn't take notes fast enough, you can also check out the monthly What's Up column in the Portland Press Herald. Bernie, could you do the honors of introducing our special guest for today?
Yes, I will. Thanks. Okay, well, we're very lucky today to have Dr. Adria Updike join us. I've known her from my astronomy club from way back when she took a science camp with one of the people in our club, and she gave us a nice presentation of her work for her PhD work, and then really haven't been in touch with her for over 20 years. So I'm glad that she said yes, that she'd be on our show and talk about all kinds of interesting things, including some of her work and some of the new things she's doing and some of the telescopes she's worked on. So I'll let you introduce yourself, Adria, and some of the things that you've done. Go ahead.
Thanks, Bernie.
You're
So
welcome.
I first got interested in astronomy thanks to your club, ASNI, at the Astronomical Society of Southern New England, when they did a star party at a science camp that I was at. And until then, I might have been interested in, say, environmental science, because that's what we were doing at the camp, and then switched overnight to astronomy after getting to look through a telescope for the first time. So I went to Smith College to study physics and astronomy, and I earned my master's and PhD at Clemson University in South Carolina in physics. And I went on to do a postdoc at NASA's Goddard Space Flight Center, where I was working in the observational cosmology lab. So I was doing computer simulations of how galaxies evolve. Then I went from there to a 1-year professorship at Dickinson College in Pennsylvania, and now I'm at Roger Williams University in Rhode Island, where I am a tenured associate professor of physics.
All right.
Wow, wait a minute. I didn't realize that you had gone to a star party when you were a child. And
Yeah.
wait, so Bernie, you were there?
Yeah, I was
Yep.
helping Pat run the telescopes. Yeah, of course.
Yep.
I didn't know exactly that's how Adria got interested either. I just knew about the club, but that's great. That's a good story.
Yeah, that's why I volunteered for every star party after that, and I've given so many of them because, hey, that's how I got into this, was looking through a telescope for the first time, and that's all it takes sometimes. So if you do
Yeah.
100
That's
star parties,
amazing.
maybe you get an astronomer out of a couple of them.
Yeah.
Wow, what a way to like circle back to to you, Bernie.
Yeah.
All thanks to you and your cohort there.
Yeah.
Absolutely.
What were and that was the first time you had looked through a telescope?
That's right.
What do
And
you
it turned out,
remember what
oh, probably Saturn. It was probably Saturn.
Yeah.
It's usually Saturn. Yeah. That's the one that really hooks everybody in.
Yeah. So, did you want to talk about some of the work you've done for your PhD thesis, Adria?
Yeah, so I studied gamma ray bursts, what we call GRBs. Gamma ray bursts were first discovered by a flash of gamma radiation. So gamma radiation doesn't make it through our atmosphere. So we didn't know these existed for a very long time. Back in the 1960s, the US government launched a series of satellites called the Vela satellites to detect gamma radiation in space. And what they were looking for were violations of the Nuclear Test Ban Treaty. They were looking to see if the Soviet Union was testing nuclear weapons in space or in the atmosphere, which was a violation of the treaty at the time, because that's a bad thing. You don't want nuclear fallout falling back into the atmosphere and circling around the Earth. So they never did see that. But what they did see were unexpected sources of gamma rays coming from somewhere else. So these satellites looking for gamma radiation were not very good at pinpointing where it came from. It was basically Earth, not Earth. And they got a whole bunch of not Earths. Fortunately, they never saw any Earths. Nobody was violating the test ban treaty. But they got a whole bunch of random flashes of gamma rays, a couple a day, coming from not Earth. So the question was, where were they coming from? Are they coming from the sun? Are they coming from the moon? Are they coming from our local area? Or are they coming from outside our galaxy entirely? Are they coming from the outside universe? And it wasn't until the launch of some later satellites that they started to pinpoint them more directly and notice that these gamma ray bursts were coming from all over the sky. So, you know, our galaxy is shaped kind of like a pancake with a lot of stuff in the middle, like a pancake if all the blueberries ended up in the middle. So if the gamma ray bursts were coming from our galaxy, they would be mostly concentrated along the disk or towards the middle, but they were coming from all over the sky. We call that isotropically. They're coming from all over the place, which means they must be coming from the outside universe if they're not preferentially coming from the disk of our galaxy. In fact, we've never discovered one in our own galaxy, and that's a good thing because it turns out these are the most energetic explosions in the universe. So if you've heard of supernovae, exploding stars, a gamma ray burst is what you get, well, sometimes, if a star even bigger than that explodes. So gamma ray bursts initiate from stars that are 40 times the mass of our sun or bigger. There's not a lot of these stars around. So fortunately, we think we could see maybe 2 a day, 1 or 2 a day from the universe. At the moment, the only satellites that do a good job of detecting them all the time can't see the entire sky at once. So based on the number they see and how much of the sky we can see, we think there's maybe 2 a day coming in from the universe. So these gamma ray bursts, there's like 3 different types of them. There's short ones where the gamma rays come out in little bursts, less than 2 seconds. There's what we call long gamma ray bursts, where they come out between 2 and about 120 seconds worth of gamma rays. Oh, wow. And then there's a brand new class called ultra long gamma ray bursts, where the gamma rays come out for a couple minutes and then could last even up to days. Wow. So after many, many years of study, the current thinking is that the short gamma ray bursts come from the collision of 2 neutron stars. So 2 neutron stars that are orbiting around each other and eventually collide and produce a big explosion. Long gamma ray bursts, which are the kind that I used to study, which are the collapse of extremely massive stars, these 40 solar masses or larger stars. And then the ultra long gamma ray bursts we think might come from tidal disruption events like black holes pulling in nearby stars, the forming of magnetars, these highly magnetically charged neutron spinning stars, things like that, really rare, weird events. When gamma ray bursts explode, when they go off, the light doesn't come out in every direction like a supernova, which explode isotropically going off in every direction. So a supernova you can see from any direction. When a gamma ray burst explodes, the light comes out in jets. And when I say light, I mean gamma rays, X-rays, ultraviolet, visible light, infrared, all the way down to the radio. It comes out across the entire spectrum. It's just that the gamma rays are how we first found them, using the gamma rays, so we call them gamma ray bursts. But that's not the only light that comes out. It all comes out at once. And it comes out in these jets. So they're emitting an incredible amount of energy, but only in very narrow jets. So you can only see one of these happening if you happen to lie along the jet, if it's pointed directly at you. Mm-hmm. So because these jets are only a couple degrees wide, we miss the vast majority of these going off. So if we see 1 to 2 a day, there's probably a couple hundred a day going off around the universe. It's just that only a couple of them were pointed directly at us. So we miss the vast majority. As far as we know, there's no other way to detect them if you're not along one of these jets.
So they're kind of like the solar system's laser beams?
That's a
right?
great
it's
way
like
to put
lasers.
it. Exactly. If you take a laser, don't do this, but if you took a laser and kind of, spun it around a bit, you'd only actually see it if it's pointed directly towards you, or if you have like chalk dust or something hanging in the air to see it along. Unfortunately, there's not a whole bunch of dust out in the universe. There's a ton of dust and gas, but it's not everywhere, so it's not going to light up when something goes by. We don't see just the edge of one of these. You either see it or you don't.
Yeah. And it seems like they're primarily associated with black holes and something happening with them, right? So either the neutron stars are rotating, and then they collapse into a black hole, or a hypernova, or the black hole's just eating other things.
Exactly. Yeah. So they're mostly, we're pretty sure they're forming a black hole after the gamma ray burst goes off. And in some cases, we've seen a supernova a few weeks later as well. So they could be the precursor. They could be the precursor to a supernova in a lot of very massive stars. However,
Gotcha.
the gamma ray burst itself is so much more energetic than the supernova that we'll often see the gamma ray burst, but the star is so far away, we wouldn't be able to detect a supernova that followed it. It would just be too dim.
Oh, wow.
So, yeah, exactly. These gamma ray bursts are often the only way we can see very distant galaxies. We didn't even know that galaxy was there until a gamma ray burst exploded in it, because it outshines the entire galaxy. But it only does it for a few seconds. These things start out very, very strong and die off very quickly. So we detect the gamma rays, but if you want to see it in the other parts of the spectrum, you have to get on it very fast. You have to take a telescope and turn it around right now. It's not enough to do it a day later. You're probably going to miss it. Now, half of them we don't see at all with any other part of the spectrum. And we think that's because there's often a lot of dust and gas around these stars that blocks the rest of the light from getting out. But if you want to catch it, you have to do it very quickly. So what I spent a lot of time in my graduate career doing was sitting at observatories waiting for a gamma ray burst to go off. So another scientist would be using the telescope, and I would be sitting there, and I'd be on my phone, and I would get a text message when our satellite in space, the Swift Observatory, detected a gamma ray burst. And we had set it up so that when one of these is detected, all these alarms in the observatory go off. Wake me up, because I was not necessarily awake when this happened, although I had to be in the room because the telescope was programmed to drop whatever it was doing and turn around and go look at my gamma ray burst instead, which you can probably imagine annoyed a lot of people because they were in the middle of doing their science and it got dropped to do my science. So I not only had to take over the telescope and try to find this gamma ray burst in the sky, I also had to sit there and justify my science to the person who just got interrupted on their program. Even though they had agreed to this when they took the time on the telescope, they just forgot that they had agreed to this. Because we were so disruptive to other people's science, I showed up at the telescope one day and there was an anthropologist there from France, and he was studying how astronomers resolved conflict. And it was basically what happens when Adria needs to take over the telescope. It was like, this is somebody else's thesis project. My thesis project interrupting other people has become somebody else's thesis project.
Did they come up with that? Like, was that a thesis that they were doing something else and then they saw what was happening and they're like, I'm going to switch my project?
It must have been like, they had a roommate who was running a telescope or something. I can't imagine. I don't know any anthropologists what they do. I don't know how they this and what we do.
I'm sure you did it in a nice way without just throwing him out of the telescope room or something.
He was nice and quiet. Yeah, he not with himself.
Sure. So, but you were looking at the long ones, right? And you said that was between 2 to 120 seconds. So, I mean, for the telescope to move around, did you ever, it would never, like, if it moved, would you miss it like that?
You could pretty fast. So the gamma rays themselves were usually gone within a couple minutes, but I was looking for the visible afterglow, and that can last a few hours to a few days. It just gets dimmer, easier to spot when it's new. So basically what we would do is we would go to the area of space, the error region of the gamma ray telescope. So we would say, hey, it was over there. So we point our telescope kind of over there. And what we're doing is we're looking for a new star that wasn't there before. So I'm sitting there going back and forth between known star chart, image of the space and like, all right, what's new? What wasn't there before? And downloading the data and analyzing it as fast as possible to try to get the deepest possible image to look for a new little blot that wasn't there before. And that's how I spent a lot of my graduate education, was running telescopes, stealing them from other people, taking pictures of the sky and looking for something that wasn't there before. And then you just take a whole bunch of different pictures and a whole bunch of different filters. So I want to look at it in the red and the blue and the ultraviolet and the green and the yellow and the near infrared. Because the balance of all of those colors, basically how bright it was in one color versus another, actually told me how much dust was in the galaxy that the gamma ray burst exploded in. Mm-hmm. So my PhD was focusing on using these gamma ray bursts as basically like kind of like turning on a flashlight in a faraway galaxy for a few minutes to a few hours. And you can see all these things you had never been able to see before, and then it goes away, it shuts off, and that's it. So we get a very quick glimpse of a very, very far away galaxy. And of course, far away means early in the universe. So a very, very young galaxy. And these are often our only glimpses of these young galaxies. And looking at how much dust and gases in these galaxies can give us an idea of how early stars evolved, because early stars are probably very different from today's stars, and we don't have a great handle on how.
Looking at these early galaxies, what were some of the conclusions that you came up with?
Oh, so gamma ray bursts can come from all over the universe, but because they come from extremely massive stars, it turns out that those extremely massive stars are very hard to produce today. So stars of 40 to 100 times the mass of our sun, for some reason, they were much easier to form in the early universe. So the early universe had a different population of stars than we do today. And it makes sense, or the only thing that would really make sense, I guess, to explain that would be what we call metallicity. So how many metals are in this star? And because we're astronomers, we consider everything other than helium and hydrogen to be a metal. So the astronomer's periodic table says hydrogen, helium, metals, everything else. Basically, yeah, so we'll call everything other than those.
A little bit different.
Yeah, exactly. Yeah. Sometimes we care about like carbon and oxygen, and silicon, but not as much. No. It's basically not there as far as astronomers are concerned. Everything is hydrogen. So, yeah. So the early universe was about 25% helium, 75% hydrogen, and basically nothing else. So when these stars were formed, they didn't have any metals in them. They didn't have anything heavier than helium in them. And for some reason, they could form much, much bigger stars and still be stable. But today, it doesn't look like we can do that. We're in like the population 2 or 3. So we're the next couple we're population 1. We're the next generations of stars. So those giant stars were very big, and very big stars run through their fuel extremely quickly. So they have very short lives. So 40 to 100 solar masses might only live a few million years before it explodes. It's in the process, and as it goes through its life, it forms heavier elements. And when it explodes, it spreads those throughout the universe. And the next generation of stars is made out of those. And the more metals they have in them, the more metals they'll form. And then you get, the next generation of stars after that. And you've got more and more heavy metals in these stars. And it looks like the more heavy metals you have in your stars, the smaller on average these stars are going to be. So you're not going to get those giant stars anymore. So this is really useful for us because when we see a gamma ray burst, we can assume it came from kind of far away. We're probably looking at a star that formed earlier than our sun. So it had to be from a very massive star, and those are very hard to form today. So usually when we see one of these gamma ray bursts, they came from an earlier population of stars. So in fact, the earliest or the farthest away things that we've ever seen, including the earliest objects we've ever seen, have been gamma ray bursts. So every time one of these explodes, one of the big questions is, how far away is this? Is this a very early universe object? And in fact, one of my teams that I was on, one of my collaborations, very briefly held the record for the furthest away object ever discovered.
I was going to ask.
Yeah,
what's
for like
the furthest you've seen?
And then Hubble took it away from us. It was, it was like a redshift 11. So redshift 1 is halfway back to the beginning of the universe. Redshift 2 is 3/4 of the way back. Redshift 3 is 7/8 of the way back. So redshift 11 is pretty close to the first population.
Wow.
Yeah, there. Yeah. So it's
Wow.
really cool to see.
Okay.
Yeah.
Yeah. So I feel like maybe I missed this, but you mentioned that we used to be, or the universe used to be able to make much larger stars, but that doesn't happen now. Why is that?
Ooh, I'll have to find you a stellar physicist to talk to about that. And
But
I'm
I
sure
guess it's
figuring out
interesting
that
that
now, but
because yeah, because that was something that you like discovered through this work, right?
it had been proposed earlier, so it wasn't a
Okay,
discovery through this work. I mean, it makes sense based on how we think the universe evolves and things like that.
gotcha.
A lot of our studies of metallicities and dust populations in these galaxies helped confirm how old these stars were, how old these galaxies were, and things like that. So it
Hmm.
led to a lot of that research. Now, the
Yeah, no,
thing for us here on Earth is that there are very few stars in our own galaxy that would be capable of producing a gamma ray burst. So our galaxy has what, 200 million,
Million.
billion,
Yeah.
billion stars, something like that. Only a couple of them that we're aware of are massive enough that they could produce a gamma ray burst when they explode.
Mhm.
Now, of course, one of the only ones that could do that, Eta Carinae, is currently pointed right at us. So if it did go gamma ray burst tomorrow, we would know about it. Because the poles of that star, one of the poles is pointed directly along the line of the Earth at the moment. So we would be right in the path of gamma ray burst if it exploded. But say a star like Betelgeuse, which also might explode tomorrow, that's not massive enough to produce a gamma ray burst. We'd see a beautiful supernova from it, but we wouldn't have to worry about gamma radiation.
Oh,
Gotcha. Actually, could I, in my research about gamma ray bursts, so one thing that I learned was I know you said that they're really, really high energy, but one source had mentioned that gamma ray bursts have more energy in a second than the sun has in its entire lifespan of 10 billion years. And I felt like everything that I was reading also talked about the destruction of life on Earth if we were to be hit with a gamma ray burst. And I think there were a couple of things that just ended on, we would die, or like our ozone, protects us from most of it, but if we had one that was close enough, we would just be wiped out. And so I know you just mentioned that Eta Carinae is pointed at us, but do you have a time frame for when that? I don't know if that's something that you could see or
Oh,
not.
when it comes to stars exploding, it's going to be soon. So anytime in the next 100,000 years or million years or so, that's soon on an astronomer's timescale. So
Yeah, soon, astronomy soon.
so if Eta Carinae did go gamma ray burst and was pointed at us at the time, it's close enough. It's still, like half the galaxy away, but it's still close enough that it would cause definitely some problems on the Earth. Yeah, so the gamma radiation can cause a buildup of nitrogen in our atmosphere. It can cause basically what would look like a minor nuclear winter. It would cause the atmosphere to darken due to the nitrogen buildup. It would be a lot harder to breathe. We'd lose a lot of the oxygen in our atmosphere. If it happened extremely close by, it could really just boil off parts of our atmosphere. And there's some people who think it might have caused a nearby gamma ray burst might have caused a major extinction event a few billion years ago on the Earth. There's some evidence that one of the extinction events, and I'm afraid I don't remember the names of all these extinction events. I did not take geology to be an astronomer. Probably should, but I didn't. One of the extinction events was fairly unique compared to the other extinction events. It seems to have mostly affected the surface life a lot more than the deeper life. Usually extinction events are
Mm.
pretty uniform. They affect everything. But one of the major effects of gamma radiation hitting our atmosphere would be a lot more ultraviolet radiation making it in. And that would have much more of an effect on the surface life than, say, things that live deeper under the ocean, because most of that would be absorbed before it got it down there. So there's some evidence that, I don't know, it seems pretty conclusive to me, but, I'm not an expert on that. Gamma ray burst, a nearby gamma ray burst may have caused an extinction event on the Earth, one of the at least 6 that we've been through. Fortunately,
Gotcha.
because that was a few billion years ago, it's harder and harder for those stars to form. So it's less and less likely that one of these is going to happen. Now, I did solar physics for a couple of years while I was in when I was an undergrad. And solar physicists can get a lot of money from the Department of Defense because a solar flare going off can affect satellites on Earth, and it's knocked out power systems. Very large solar flares have knocked off power systems. They can throw off the GPS of planes and ships and cause oil spills and planes crashing and things like that. So it's really good to know if one of these things is coming, a solar flare, that is. However,
Right.
there's really no way to predict if a gamma ray burst is coming. The solar flare.
I was going to say, do you have a contract with the Department of Defense yet?
I do not,
No.
unfortunately. With the solar flare, it takes a little while for the material to get to the Earth. So you see the flare explode on the sun. 8 minutes later, the light hits you from the sun, but it takes a couple of days for the actual particles to arrive, and they're the ones that cause the damage. With the gamma ray burst, it's all light. We're not getting any particles. We're just getting all the light, and all of it shows up at once because all types of light travel at the same speed. So unfortunately, you can't really predict when they're coming. You also can't say, well, it's going to hit the other side of the Earth, so it doesn't matter. It's going to hit all of us at once. It's not selective. Yeah, it's not like, oh, that just hit, I don't know, Russia or something. No, it's going to cause the same problem everywhere. Yeah.
Huh. Interesting.
Now, it would be a really cool way to go, and a very bright way to go, but it's going to knock out everybody.
You mean a cool way to die, or?
Yes, that's what I'm thinking. Yeah, it would be a cool way to die.
Make a good movie. You should make it.
If I had to pick a way to die, I'm not going to.
Bernie, if we get hit by it, we'll be dead. Nobody will be making that movie.
Like we have movies on, 2012 and the.
Like a predict.
And all those. We should make a movie on that. I haven't seen that scenario yet.
I don't know. Maybe if it was even slightly scientifically accurate, it'd be like, and then everybody's gone.
Yeah, it'd be a pretty sad movie. Like no growth, no. I don't know. There was one also comment about gamma ray bursts where they had thought that maybe because of gamma ray bursts, why it's so difficult to find life on other planets or in other galaxies. I don't know if you've come across anything like that, because the justification was that in some other places might have been hit more, or maybe seeing them more. And so life just keeps getting eradicated over and over again.
Yeah, I have seen that theory, and it's really an interesting idea. So again, the further we look out in the universe, the further we're looking backwards in time. So when we look at the Andromeda galaxy, we're seeing it as it looked 2.5 million years ago, not as it looks today. So the further out we look, the more galaxies we see, the earlier they are in their evolutionary stages, and the more likely it is that they have these stars that can go gamma ray bursts. Now, if you have nearby stars producing gamma radiation on a regular basis, it's really hard for life to exist on these planets. Gamma radiation as we know it would wipe out anything on Earth if we didn't have an atmosphere. And then it's going to cause a lot of the ultraviolet radiation to get in. So having life like ours is going to rely on not a lot of gamma ray bursts going off in your galaxy or in nearby galaxies. So the theory goes, it's hard for life to really get a foothold in galaxies early on because they might be constantly getting bombarded by gamma radiation every million years or so and wiping out whatever had been there at the time. And they've basically got to start over again. So it's an interesting theory. I know a lot of people calculated in when they talk about how likely it is that there's intelligent life out there. Now, once a galaxy reaches the age of our Milky Way, at this point, we've got almost no gamma ray bursts going off, so we don't have that problem to worry about. But we're also kind of far out towards the edge of the Milky Way galaxy. We don't have a ton of nearby stars going supernova and also producing, say, a lot of ultraviolet radiation and X-rays and things like that we need to worry about. We don't live in a globular cluster surrounded by very nearby stars that could also be throwing out solar flares and things like that. So yeah, we're in a pretty safe part of a pretty well-evolved galaxy. Douglas Adams would put it, well out in the western spiral arm of an insignificant part of the galaxy. That's where we are, fortunately. So yeah, it's very likely that galaxies in an earlier formational stage, like the ones we see when we look out in space, might be at a point where there's still too much harmful radiation for life to really get a good foothold. We might have to wait a lot longer. But then, given the speed of light, even if we did detect a signal from Andromeda, it's not like we could hold a conversation if it's going to take 2.5 million years to send a signal, and then we'd have to wait 5 million years for them to send something back. Not all that feasible.
Fair. I think hopefully listeners' fears of being destroyed by a gamma ray burst have been allayed with that.
It is extremely unlikely to happen, but if it does, there's nothing you can do about it. So.
Yeah, I was gonna say, what would an escape plan be? Because there's no.
No, if it's hitting us and coming from somewhere else in our galaxy, it's going to hit our entire solar system. It's going to take out everything nearby. So, yep, no escape plan. If it happens, it happens. It's not worth worrying about. It doesn't keep me up at night. I got
All right, so we can take that off of our worry list.
There are much better things to worry about.
This conversation with Dr. Updike was part of a longer conversation from 2 other shows. If you want to catch the full conversation, we'll link to it on our Twitter and also on our YouTube page. You've been listening to Scientifically Speaking here on WMPG with myself, Bernie, and Dr. Updike. From your favorite nerds, mask up, and we wish you healthy bodies and clean air.